So this is case study number 5, in which we are going to see how flanges improve the stiffness and strength of sheet metal brackets. So this is a very simple L-shaped sheet metal bracket which is having two holes as shown over here. One hole will be fixed, another hole will be loaded with 500 Newton force. So in the model, in the FEA model, the hole over here, the surface of the hole, internal surface of the hole will be loaded with 500 Newton, and this internal surface of the hole will be fixed in all degrees of freedom. So these are some reference dimensions, 90 mm and 90 mm. Height is 90 mm, width is 90 mm. So with this analysis, these are the results. We will see that the stress generated is 196.8 megapascal over here. So 196.8 megapascal stress is generated considering the steel as material, and the deflection over here is 0.4766 mm. So the end deflection of the bracket with this setup is 0.4766 mm. Let's see how to improve the design. So the first design change which we'll be making over here is to add a dimple. So a dimple is basically a depression on the bend of the sheet metal bracket as shown over here. These dimples are added to improve the stiffness of sheet metal bracket. So let's see what is the effect of the adding a dimple on this L-shaped bracket. So if you add the dimple and rerun the analysis, we will find that there is 5% reduction in stress. So 189.3 megapascal, and the stiffness increases by 15%. That is, the deflection reduces by 15%, 0.4072 mm. The next design change is adding a flange. So if you add the flanges to the edges of the bracket, that will greatly reduce the stress and also greatly improve the stiffness. So there is 48% reduction in stress from the base design, 101.9 megapascal, and 62% increase in stiffness because of addition of these flanges. Now if we are creating an all-round flange, that is even these edges we are combining with the flange, so the design will look something like this. And if that's the case, then we get further reduction in stress, that is 50% reduction in stress and 65% increase in stiffness. So the addition of the flange will greatly improve the performance in terms of the stress as well as the stiffness of the bracket. Continuing with sheet metal brackets on how flanges improve stiffness and strength, let us have a look at this case study number 6, which is the stabilizer bar clamp bracket. So stabilizer bars are components which are used in vehicle suspension systems to balance the movement of the left and the right wheels. So these stabilizer bar, as highlighted over here, will have a clamp bracket which attaches that stabilizer bar to the frame or chassis of the vehicle. So that is the case study which we are going to look at. So the clamp bracket is generally in this shape, which has two mounting points and a depression over here in which the rubber bush of the stabilizer bar goes in, and the rubber bush impinges a force on the inside curved elements of this clamp bracket, and these faces, these mounting faces which are used to fasten the clamp bracket onto the frame or chassis, these are fixed surfaces. We are going to consider these surfaces as fixed in the analysis, and we are going to analyze for 2000 Newton force and how to improve the design. So for this bracket, the weight is 157.5 grams. Material is sheet metal steel, basic steel. And if we run the analysis for this bracket, we will get a stress of 49 megapascal at this area, which is the fillet. So at these areas, we will get 49 megapascal, and the deflection will be maximum at this point. So that is 0.00983 mm. Now we are adding a 7 mm flange on the edges. So by adding the flange, the stresses will reduce and so will the deflection. The deflection will also reduce, the stress will also reduce. So the stress in this area is 38 megapascal and stress in this curve is 58 megapascal. And the weight of the bracket has increased 168 grams, and the deflection is also reduced 0.008177 mm. So adding a 7 mm flange as shown will greatly improve the stiffness and reduce the stress. Here at this spot, there is a high stress point which is 58 megapascal. We can reduce this by adding material over there. So by modifying the design of the flange and creating a smoother radius at that point, we can reduce the stress at that point to 44 megapascal. So with this new improved design of the flange, which is having a smoother radius at the point of high stress, we have reduced the stress to 44 megapascal from 58 at that point. And over here also on this fillet, it will be 30 megapascal. So the weight is 173 grams and the deflection is 0.006879 mm. So this is an optimized bracket for the application.